Hi everyone, this is Professor H. Rahman from Agricultural and Food Engineering Department, IIT Kharagpur. I welcome you all to this NPTEL online certification course on traction engineering. This is lecture 17 where I will try to cover how to find out tractive effort and slip of a pneumatic wheel. When I said it is a pneumatic wheel, so the obvious questions which will come to our mind is whether it is operated in rigid mode or whether it is operated in elastic mode. So now the concepts which will be covered will be tractive effort and shear displacement. As you know that tractive effort is related to shear displacement, hence we will cover these two concepts with respect to pneumatic wheel. Now, if you look at these two wheels, both are pneumatic wheels, but one is written as rigid mode, the other one is written as elastic mode. The difference is when the pressure due to carcass stiffness and pressure due to inflation of air or air inflation pressure, when the summation is greater than the pressure which the terrain can support at the lowest point of the tire circumference, then the tire will remain like a rigid wheel. It will remain round like a rigid wheel. So that means this will behave like a solid toed wheel or solid powered wheel. Now when that wheel is powered, it becomes powered wheel. So now our discussions will be confined to powered wheel as we are interested in finding out tractive effort. Now the second option is elastic mode. Again the inflation pressure and the pressure due to carcass stiffness, if it is less than the pressure the terrain can support, then the tire will be flattened at the contact point. So this condition is called elastic mode. So these are the two conditions which are shown in the right corner. One is rigid, where the circumference of the tire is perfectly round, whereas in the second case it is not round, rather it is flattened at certain portion. So if it is in rigid mode, how to find out the tractive effort? If it is in the elastic mode, how to find out the tractive effort? That we will discuss separately. Now when it is in rigid mode, as I said, this will be equivalent to a powered rigid wheel. And for powered rigid wheel, the main thing is tractive effort, which we have already derived. So we will follow the same procedure. So when we talk about tractive effort, that means what is the shear stress which is developed, and shear stress is a function of shear displacement. Where it is developed? It is developed at the contact patch, where the wheel is in contact with the soil. So this is the phase where the shear stress will be developed. Now to find out shear stress, we should know what is the shear displacement, and to know the shear displacement we need to know what is the slip velocity. So these are all interlinked. So what is slip velocity? Slip velocity is the difference between the theoretical speed Vt and the actual speed V. So if you consider a point here as A, then at that point the theoretical speed will be Vt will be equal to omega r. If r is the rolling radius, omega is the angular speed, then Vt will be equal to omega r, and the actual velocity is V. Now if you take a tangential component here at the point A parallel to Vt, then V will be the component will be V cos theta, because you have considered the point A at an angle theta. So Vt minus V cos theta will be equal to your slip velocity Vj. So you have to analyze this slip velocity, how it is varying, or from there we will find out what is the corresponding shear displacement, and then we try to correlate the shear stress with shear displacement. Now for finding out the shear displacement from the slip velocity, we know that shear displacement will be equal to x into Vj. So if I take this one, Vj is equal to Vt minus B cos theta, I take Bt common, then it becomes 1 minus B by Bt cos theta. Now B by Vt is nothing but slip I. So indirectly I can write that Vt 1 minus I cos theta, and Vt is equal to omega r. So omega r 1 minus I cos theta. Now this is at the point A. Now if you want to find out throughout the contact surface or from the contact surface from A to the point where the wheel is just entering the soil, if you denote it as B, then this has to be integrated. Okay, this has to be integrated from theta to theta 0. So by doing that, we will finally develop equation for shear displacement. J is equal to r into theta 0 minus theta minus 1 minus I into sin theta 0 minus sin theta. That means displacement is a function of the entry angle theta 0, which is denoted here, which is shown in this figure, and theta 0 is called the entry angle, and theta the point where we are interested. Now once we know the shear displacement, next thing is how to correlate this shear displacement with shear stress. So in nature, what we have observed is there are three different categories of relationship available or found. One is related to loose soil, the other one loose soil or saturated clay, and in disturbed soil, and the other one is in organic terrain, then the third one is in compact sand, silt and loam. So these are the three relationships which we have discussed earlier, and the relationship in these three conditions like loose sand, saturated clay, tau will be equal to, that means shear stress is equal to maximum shear stress into 1 minus e to the power minus j upon k, where maximum shear stress is described as C plus sigma tan phi. That means it is a function of cohesion, it is a function of angle of internal friction of soil and the normal stress which is prevailing. So C plus sigma tan phi into 1 minus e to the power minus j upon k. Now in case of organic terrain, tau is equal to tau max into j by kw into e to the power 1 minus j upon kw. So this kw is nothing but the shear displacement where the maximum shear stress occurs, and the third relationship is tau is equal to tau max into kr into 1 plus 1 upon kr into 1 minus 1 upon e minus 1 e to the power 1 minus j upon kw into 1 minus e to the power minus j by kw. So these are the three relationships available. So now depending on our soil condition, we have to select one relationship. Then once you select the relationship, next is how to find out shear stress. So shear stress which will be developed at the curved portion will be equal to tau, I have indicated as tau theta here, because from which angle we are going to, what is the distribution of shear stress, that is important. So tau theta is equal to tau max into 1 minus e to the power minus j upon k. Now again I replaced tau max, I have taken this for the loose sand or the saturated clay, so C plus sigma tan phi, again sigma phi I have taken as sigma theta, knowing we have to know the pressure distribution, whether it is constant or it is varying. So all those factors will come into picture. Now I replace that displacement with the equation r into theta 0 minus theta minus 1 minus I into sin theta 0 minus sin theta. So this will be the final expression for shear stress. But shear stress is not important. What we are interested is to find out the shear force. So in a solid wheel or rigid wheel, shear force will be equal to So these are the shear stress. So now to find out the shear force here, so I have to multiply with the area. So area, so we have considered a point A. So area of that elemental area dA will be equal to, if B is the width of the wheel, B into r d theta. Now this has to be integrated. So tau theta into dA will give you thrust force. So RB tau theta d theta, this will give the shear force, but we are not interested about the shear force, we are interested in finding out the thrust, which is the horizontal component of shear stress, shear force which is developed at the contact patch. So this is your F, this is your shear force. So horizontal component will be F cos theta, Fc will be equal to F cos theta. So this has to be multiplied RB tau theta into d theta cos theta d theta. So this has to be integrated from theta to theta 0, depending on in which area you are interested to find out the thrust force. So this will be the expression for finding out thrust in case of a pneumatic wheel when it is behaving like a rigid wheel. That means it is moving in a rigid mode. Now the other mode is elastic mode. So let us see now what happens to the elastic mode. A part of the wheel will be flattened and the another component which will be curved one. That means we have to consider the shear displacement along the flat portion, we have to consider the shear displacement and the curved portion. So I have differentiated or demarcated, we can say, the flat portion as AB and the curved portion as BC. Now to find out the shear displacement or shear stress on the flat portion, we need to know what is the shear displacement in the flat portion, and similarly for finding out the shear stress on the curved portion, we have to find out what is the shear displacement in the curved portion. So if at B the total shear displacement is denoted as JB, and which is denoted as JB, and at a point suppose X starting from point B. So if we are interested in finding out what is the displacement at this point, then I have denoted that as delta J. So total displacement up to point X will be JB plus delta J. Okay. So this Jx is nothing but the cumulative shear displacement at a distance X from the point B. Now we will consider two things, one is the curved portion, the other one is the flat portion. Let us now see how do we develop this shear stress in curved or flat portion. Now let us come to the flat portion. So basically we want to find out the slip velocity if the truck is moving in at a velocity, actual velocity v, and Vt is the theoretical speed of the truck, then Vt minus Ba will give you this speed of slip of the truck, if which is denoted as Vj. If its direction is opposite to the direction of forward movement, then it is positive. Okay, and if it then it is called slip. If it is opposite to the theoretical the actual speed direction of travel, then we take as skid. So here the theoretical speed is nothing but omega into r, where omega is the angular speed of the sprocket or the driver which is driving the truck, and r is the rolling radius of that driver. Now shear displacement, which is denoted as Jx at a point located at a distance x from the frontal area of the contact area. frontal portion of the contact area. So that becomes, if you know the slip velocity times t, then that will give you what is the shear displacement during that time. So Vj into t, and t is equal to x by Vt. So t is the duration for which the track is in contact with the soil, or the link is in contact with the soil. So now shear displacement will be equal to Vj by Vt into x, and Vj by Vt is nothing but your slip. So it is basically slip into the distance from the front end of the track. Now if you are in, so that means the flat portion will behave like a track, and the shear displacement will be calculated or computed as you have followed for computing the shear displacement in case of a track. So in a pneumatic wheel, we will consider that shear displacement in this flat portion will be equal to I into x. Now the total length, if we denote as L, which is the contact length. So if this is the contact length, then total displacement will be I into L. If you are interested up to this point, then the distance you have to know. So at x, it is written as Ix. And we have already known that the displacement at point B, because of the curved portion, this is the displacement. So the total displacement will be again summation of Jb plus summation of IL. Now next thing is, only shear displacement will not help you. We have to find out what is the shear stress which is prevailing under the flat portion as well as on the curved portion. So for the curved portion, again we have to find out what kind of soil is there. If it is a loose soil, if it is a organic terrain, or if it is a compact sand, then we have three different kinds of relationship available. So based on that, we have to find out the relationship between shear stress and shear displacement. So in this case, I have taken the loose sand, where tau theta is equal to tau max into 1 minus e to the power j b upon k. Displacement and the curved portion divided by k, shear deformation modulus k. Now if you know the normal distribution, then tau max I can write as c plus sigma tan phi or sigma theta tan phi into 1 minus e to the power minus r upon k into theta 0 minus theta. So theta 0 is entry angle, this is your theta 0, and theta is, that means corresponding to point B, the angle is theta from the vertical, and corresponding to point C, the angle is theta 0. So now the displacement I have replaced, JB I have replaced with R into theta 0 minus theta 1 minus I into sin theta 0 minus sin theta. So this will be the expression for shear stress. Now next thing is, what is the shear force which is acting? So shear force will be again acting tangent to this surface, okay, the contact surface, suppose at point P. Now the shear force will be equal to whatever shear stress we develop multiply with the area. Area will be equal to RB d theta. So this has to be integrated from theta to theta 0, from theta to theta 0, okay. So that will give you the value of shear force, and the cost component of that will be taken to find out the tractive effort. So tractive effort will be this RB tau theta cos theta d theta. So this has to be integrated from theta to theta 0. So that will finally give you what is the tractive effort. That means now you have found out tractive effort at this point because of the curved portion. Now again for the flat portion, we have to find out the suitable relationship. If it is a loose sand, then again we take tau theta will be equal to tau max into 1 minus e to the power j x upon k. If you are interested to find out shear stress up to the point x from the front end of the flat portion, then I replace tau max with C plus sigma theta tan phi, and that into 1 minus e to the power minus ix upon k. So, I have replaced this jx with ix. Okay. Now, since we are interested for the total length, so that means this will be equal to IL, okay, e to the power. So, this will be equal to this, instead of x you can take L. Now, the thrust force developed will be, this has to be integrated from this point to the end point, that means from point B to the point A. Okay. So, I have multiplied the area with the shear force. So, that means B into dx, the area that has to be integrated from 0 to L. So, this will give you thrust force for the flat portion. So, now the total thrust force will be the sum of the thrust force which is developed on the curved portion, sum of the thrust force which is developed at the flat portion. So, this is the final expression. Okay. So, that means up to this point we are considering. So, from here to here, then from C to B and B to A. So, finally, the total thrust force will be RB theta into tau theta into cos theta tau theta into cos theta d theta. This is to be integrated from theta to theta 0 plus b into 0 to L tau theta dx. This will be the final expression. So, what we come to know that the important thing in case of a pneumatic wheel is what is the mode of operation. Once we decide the mode of operation based on what is the pressure which is exerted on the ground and the pressure which the ground can sustain, then we decide what is the mode of operation, whether it is in rigid mode or whether it is in elastic mode. So, once it is decided, then it becomes easier for us to find out the thrust force which is developed. So, the procedure is, first if it is a rigid mode, then first find out, because the soil will behave like a rigid wheel without any deflection, then we have to follow the same procedure what we followed for rigid wheel. So, you have to find out the shear stress shear displacement relationship. So, before that we have to find out the shear displacement taking slip velocity, and from there once you find out the shear displacement, then we have to select a suitable relationship depending on which soil conditions the wheel is operated. Now, after getting the suitable relationship, then we find out the shear stress which is developed, and then the shear stress has to be multiplied with the contact area. Knowing the width and radius, we can find out the contact area, and this has to be integrated for the portion which is inside the soil, so that we can find out the thrust force. If it is in elastic mode, then there will be two sessions in the sense we have to find out for two sections. One is the curved section, the other one is the flat section, and the curved section will follow the same way as we followed for the rigid wheel, and flat portion will follow the procedure which we followed for finding out the shear displacement in a track. Basically, it is linearly related. The shear displacement is linearly related to slip value and the distance from the front end of the track. So, once it is decided, the next thing is what is the shear stress shear displacement relationship. Now, taking both shear stress shear displacement relationship, we find out what is the shear stress, and then it has to be multiplied with the area to find out the shear force. So, in the curved portion, the shear force is acting at an angle. So, the cos component, that means horizontal component, has to be found out, and then this has to be added with the flat portion to finally get the total tractive force which is developed by a pneumatic wheel in elastic mode. So, we need to know the relationship. The important things are we need to know the relationship and the pressure distribution beneath the curved portion or beneath the flat portion. Then only we will be in a position to carry out this integration. Okay. I hope I have clarified, and I have made an attempt to clarify all these things, and you will be in a position to derive equations for predicting shear displacement, and from there we can find out what is the tractive effort of a pneumatic wheel. Thank you.